Hello class, today we are going to cover section 7.5, properties of exponents and scientific notation. So, we're going to cover identifying the base, an exponent, and an exponential expression, and evaluate exponential expressions with natural number exponents, interpret the use of zero and negative integer exponents, apply the product, quotient, power, and special rules for exponents. We'll also convert a number in standard notation to scientific notation, and a number in scientific notation to standard notation, and compute with numbers in scientific notation. Let's start with the exponential expression. If a is a real number and n is a natural number, then the exponential expression a raised to the n is defined as a raised to the n equals a times a times a times dot 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 times a. Basically n factors of a. Number of a is the base and n is the exponent. So for instance here, if we had say a to the fifth, that would be a times a times a times a times a. Just multiplying 5 a's. Alright, so let's evaluate each of these expressions. A says 5 squared. Well, 5 squared is the same thing as 5 times 5. Okay, multiplying two 5's here. 5 times 5 is 25. Now, a little trickier when it gets to negative numbers here. We've got negative 2 raised to the fourth. Keep in mind that the negative 2 is in parentheses, so that negative is included in that entire multiplication chain. So I need to multiply 4 negative 2's. So 1, 2, 3, 4 of them. All right, that's negative 2 times negative 2 times negative 2 times negative 2. Now the first two negatives cancel themselves out. The last two negatives cancel themselves out. So everything here is positive. 2 times 2 is 4, times 2 is 8, times 2 is 16. Then we have negative 2 to the fourth. This one looks really similar to the previous problem. The difference here is the negative is not included. Okay, it doesn't have parentheses around it to show that it's included in this exponent. So it's not. If it's not included with the parentheses, then it's not included. So we just leave it out front. Negative 2 to the fourth is essentially negative all by itself, and then we're just working on the 2 to the fourth here. So we need to multiply 2 4 times. 1, 2, 3, 4. 2 times 2 is 4, times 2 is 8, times 2 is 16, and it's negative because that negative stays out front. So negative 16 is our answer. Let's look at the product rule for exponents. If m and n are natural numbers and a is any real number, then a raised to the m times a raised to the n is the same thing as a to the m plus n. Okay, same base here. If they're multiplied and you have the same base, you're able to just add the exponents. Okay, so let's apply the product rule in each of these cases. Case number 1, I have 5 squared times 5 to the fourth. Same base, our base here is 5, so I should just be able to add these exponents, 2 plus 4. So it's the same thing as 5 raised to the 2 plus 4, which is 5 to the 6th power. The next one, I have x squared times x to the fourth times x to the third. Same base, our base in this case is the x. Okay, so I should just be able to add these exponents, 2 plus 4 plus 3. That should give me 9. Okay, so this is the same thing as x to the 9th power. Now on C, we get a little more complicated because we've got several bases here. Okay, now the first thing you'll notice is that what we do is just go ahead and multiply out the regular numbers. So the regular number here, 4 and negative 2, 4 times negative 2 is negative 8. That's where that came from. But then we're able to combine the stuff with like bases here. I have an m squared and an m to the fourth. Well, that's the same thing as m to the 2 plus 4, which is m to the 6th. That's where that term comes from. And all these are multiplied. Okay, then I have an n to the third times n to the fifth. So 3 plus 5 is 8. So it's n to the 8th. That's where that term comes from. So the overall simplification of this is negative 8 times m to the 6th times n to the 8th. Now what happens if we have a 0 in our exponent? If a is any non-zero real number, then anything raised to the 0 power is 0. So it doesn't matter if it's a 5 to the 0 power is 1. I might have just misspoke there when I read the definition. Anything raised to the 0 power is 1. Okay. And that is a 0. So even if you had 18 raised to the 0 power, that would still be 1. Okay, so let's try some of these. 5 raised to the 0 power, just did that one. Anything raised to the 0 power is 1. How about negative x raised to the 0 power when we're guaranteed that x isn't 0? Now, a little careful here, because remember how those parentheses works. That negative is not in the parentheses. So, because that negative is not in the parentheses, it stays out front. So negative x to the 0 power is negative 1. Because the x to the 0 power gives you the 1 part. But if you throw that negative out front and you don't put it in a parentheses, that negative has to stay out there. Okay. How about 3 to the 0 power plus 11 to the 0 power? 3 to the 0 power should be 1. 11 to the 0 power should be 1. So this answer should be 2. Easy enough. For any natural number n and any non-zero real number a to the negative n power is equal to 1 over a to the n. Okay, so we can basically make your exponent positive by bringing it down here. Okay, so let's write the following expressions with only positive exponents and simplify. So ideally here, 2 to the negative third power, if we follow our definition, should just be 1 over 2 to the third power. And if we simplify that, 2 to the third, 2 times 2 times 2 is 8. How about b here? It's got this whole thing. It's got 5 times z squared 5 times z squared raised to the negative 3. I want to get rid of the negative in the exponent, so I just have to take that whole thing down, just like we did here. 1 over 5 times z squared raised to the third power. Then here I have 5 times z raised to the third power. Notice the negative 3 here is not actually on the 5 because there's no parentheses here. In order for it to be included on the 5, like it is down here, that 5 would have to be included in the parentheses. So because it's not included in the parentheses, technically the only thing that the negative 3 goes for here is the z. So in order to make that exponent positive, we're just going to bring the z down, just like you see below. So that's 5 over z to the third. All right, special rules for negative exponents. If a is not equal to 0 and b is not equal to 0, then 1 over a raised to the negative n is the same thing as a to the n. So it can work in the other direction too. So if you have a negative exponent in the top, we were supposed to bring it to the bottom. If you have a negative exponent in the bottom, you're supposed to bring it to the top. Okay, so simply changing positions from top to bottom can change you from a negative to a positive in either direction. Okay, and a to the negative n over b to the negative m is the same thing as b to the m over a to the n. Notice we just changed positions here to get both positive exponents. So let's evaluate each of these expressions. If we look at a here, we've got 1 over 3 to the negative 2 power. Well, first thing we're wanting to do is bring it up so that I can have a positive exponent. That's going to give me 3 squared. 3 squared is 3 times 3, which is just 9. Okay. B is a little more complicated. I have 4 to the negative third power over 5 to the negative 2. What I'm going to want to do is make both of those exponents positive. So I'm going to bring the 5 squared up, and I'm going to bring the 4 to the third down so that I'm able to have positive exponents on both. Now 5 squared is 25, 4 to the third. 4 times 4 is 16, times 4 is 64. And there we have it. The answer is 25 over 64. Now let's look at the quotient rule for exponents. If m and n are integers and a is any non-zero real number, then a raised to the m over a raised to the n is the same thing as a to the m minus n. Okay, and we can actually kind of see this property if we bring them on the same plane. Okay, so if I wanted to, I could rewrite this a to the m times a to the negative n. And I could follow my multiplication rule, it just says I can add the exponents here. So I'm looking at a to the m plus negative n, which is essentially the same thing as a to the m minus n. And that's why this property holds. This is your quotient rule for exponents. It has to have the same base a, right? But if it does, I can just subtract the bottom number from the top number. Okay, so let's apply this quotient rule for exponents. Here I have 3 to the 8th power over 3 squared. Well, I can just subtract those two, the 8 minus 2, and I get 3 to the 6th power. Now here we want to keep positive exponents. So what I'm really looking for is the exponent that is biggest positive. Okay. Now here that's the 8. So instead of bringing the 8 up and subtracting it from 5, which would leave me with a negative exponent that I would have to bring back down, what I could actually do is just rewrite it as 1 over x to the 8 minus 5, which obviously reduces to 1 over x to the 3rd. All right. Now, I made the big deal about biggest positive exponent because in this next case, I have z to the negative 3 over z to the negative 7. Now, both of these are negative exponents. If I move the negative 3 down and make it positive, I'm still going to have a negative exponent in the denominator. I don't want that. So what I'm going to do is move the negative 7 up, which will make it positive, which will give me a positive exponent overall because the 7 will be bigger than the 3 up in the top there in the numerator. So it's going to look like z to the negative 3 plus 7, which is just z to the 4th power. Now, let's look at power rules for exponents. If a and b are real numbers and m and n are integers, then a raised to the m raised again to the n is the same thing as a raised to the m times n. Okay. If a and b are multiplied here and raised to the m, it's the same thing as a raised to the m times b raised to the m. And if I have the fraction a over b all raised to the m, that is the same thing as a raised to the m over b raised to the m, as long as b does not equal 0. If a is not equal to 0, b is not equal to 0, and n is an integer, then a to the negative n is the same thing as 1 over a all raised to the n. And a over b raised to the negative n is the same thing as b over a raised to the n. Okay, a lot of properties here. Let's write the following expression with only positive exponents and then evaluate. Let's see here. I have a negative exponent here outside. It's 3/5 raised to the negative 3, okay, or negative 3rd. Now, I could use my property and just flip it 5/3 raised to the positive 3. That's perfectly fine. And then 5, this is basically the same thing as 5 to the 3rd power over 3 to the 3rd power. 5 to the 3rd power is 125, and 3 to the 3rd power is 27. All right, now let's delve a little bit into scientific notation. A number is written in scientific notation when it is expressed in the form a times 10 to the n, where 1 is less than or equal to the absolute value of a is less than 10, and n is an integer. Basically, in scientific notation, your number out front here, the smallest it can be is 1, but it should never be any bigger than, it can't be 10 and it shouldn't be any bigger than 10. So it has to be strictly less than 10. A number between 1 and 10, 10 not included. Okay. So if I wanted to convert, for our example here, 8,000 into scientific notation, what I would need to do is essentially break that 8,000 down into an 8 times 1,000, where 1,000 is the same thing as 10 raised to the third power. Okay, what a lot of people might see this done too, or might have been taught this, which is fine, is you take the decimal, which would be behind the 8 here, we move it 1, 2, 3 places to the left so that we get 8.0, and because we moved our decimal 3 places, we're going to multiply it times 10 to the third power because we moved it 1, 2, 3 places to the left. All right, now, so let's look at converting to scientific notation. We want to position the decimal point. Place a caret to the right of the first non-zero digit where the decimal point will be placed. I want to determine the numeral for the exponent and count the number of digits from the decimal to the caret. This number gives the absolute value of the exponent on the 10. We need to determine the sign for the exponent. Decide whether multiplying by 10 to the n should make the result for step 1 larger or smaller. The exponent should be positive to make the result larger. It should be negative to make the result smaller. Okay, so let's convert each number from standard notation to scientific notation. So here we go. This is where we're starting at. That's our little decimal place. We're going to move it 1, 2, 3, 4, 5, 6 places. Okay, 6 places here. All right, so we should have a 4.5 times 10. Because we moved it left, it's going to be a positive 6. Now for B, we're moving it right. So we're starting here. We're going 1, 2, 3, 4, 5. We'll put our new decimal there. So it should be 3.4 times 10 to the negative 5. Now, left, positive exponent. We'll move our decimal to the right. It's a negative exponent. Okay. And you can see how that works. All right, converting from scientific notation to standard notation, multiplying a number by a positive power of 10 makes the number larger, so moving the decimal point to the right if n is positive is 10 to the n. Multiplying by a negative power of 10 makes the number smaller, so we move the decimal point to the left if n is negative in the 10 to the n power. If n is 0, we leave the decimal point exactly where it's at. Okay. We want to now convert each number from scientific notation to standard notation. So for A, we have 1.97 times 10 to the 5th. Okay. Now, what we're going to do here is 1.97. Because it's a positive exponent and we're kind of working backwards now, we're actually going to move it to the right. 1, 2, 3, 4, 5. This is where it would be. In every one of these empty little circles we have here, we're going to add a 0 for. Okay. Now 3.8 times 10 to the negative 3. If I start with 3.8, negative 3, and I'm converting back, I'm moving it to the left. 1, 2, 3. New decimal should be here. Like I said, for each one of these little loops here, I'm going to throw an extra 0 in. So it should be 0.0038. Okay, negative 4.5 times 10 to the 0. Well, if it's 10 to the 0, I don't move my decimal at all, so it should just be negative 4.5. Now, let's try to evaluate this one using scientific notation. Okay, I've got 1,920,000 times 0.0015 divided by 0.000032 times 45,000. Okay. Now, what we're going to want to do here is convert everything to scientific notation, because that's going to allow us to take these tens and use our property of exponents to combine them to make all of this multiplication a lot simpler. Okay. So here I would change this one. 2, 3, 4, 5, 6. I would change this one to 1.92 times 10 to the 6 because I had to move the decimal 6 places. This one I would change to 1, 2, 3. So 1.5 times 10 to the negative third because I had to move it to the right. This one I'm going to have to go 1, 2, 3, 4, 5 5 places to the right, so it would be 3.2 times 10 to the negative 5. And this one I'd have to go 1, 2, 3, 4. So it would be 4.5 times 10 to the 4th. Like I said, what that allows us to do is now, at least on a line-by-line basis, I can combine these two. Because this is essentially 10 to the negative 5 times 10 to the 4, which is the same thing as 10 to the negative 1 power, because I can just add negative 5 plus 4, and that's where I can get 10 to the negative 1 on the bottom. I can go across the top here. Now I'm looking at 10 to the 6th minus 3. So this top should be 10 to the 3rd power. Now I've got something that looks like 10 to the 3rd power over 10 to the negative 1. If I move this up, it's going to actually look like 10 to the 3 plus 1, which is 10 to the 4th power. Now, I essentially have all of these decimals still. I still have the 1.92, the 1.5, the 3.2, and the 4.5, but I've gotten rid of a lot of extra digits here. So if I can just work out what 1.92 times 1.5 divided by 3.2 times 4.5 is, I can multiply that times 10 to the 4th and have my answer. Okay. If we can use a calculator here, that's what I would highly recommend. I wouldn't recommend doing this part by hand. But use your calculator and multiply 1.92 times 1.5 divided by 3.2 times 0.45. You should get 0.2. Now that's times 10 to the 4th power. So if I do 0.2 times 10 to the 4th, essentially what I'm doing is taking that 0.2 and I'm moving it 4 times to the right. 1, 2, 3, 4. 1, 2, 3 to fill in the empty holes here. So I'm really looking at 2,000. Okay, so I'm looking at 2,000, and this really complicated scientific notation problem turned out to be something fairly simple. Now that completes this lecture. If you have any questions, don't hesitate to reach out and email me. Other than that, I will see y'all next lecture.